Hello everybody, welcome. Well, we're the last of the day, so they're putting the time there, but maybe as we can go a little bit over. So I don't think we're going to have a problem. Today's talk, we're going to talk about Postgres and how we can...
Just time.
And here we go, just the timer. So we're going to talk about costs and data modeling. As I was saying, this title is a bit misleading. We're not going to we're kind of modeling data here. By the end of the presentation, we should be able to save some percentage of disk space, right? Our goal is we're going to start with a table. I have a table here with one or a few million rows. And this table in disk, it has about 75 megabytes. We're going to change this table, but we're going to keep all the data, and I want to keep this table to less than 65 megabytes. So is that possible to do in Postgres or whatever other database? We're not going to change any data. The data is going to be the same. I'm going to copy the data from the original table using a select star to the other table. So we make sure that we have the very same data, the very same order with everything, indexes or whatever we have from the table. So this is what we're going to do. I'm also going to show you how we can improve performance on the database. Just changing the query. I'm doing a pro bono training online on Postgres. So I found that there are a lot of companies, they need to hire DBAs, and there is no DBAs in the market. And a lot of people, they haven't been to college, or they don't have money to pay for a DBA training, right? So what I'm trying to do is, we're going out there, and we're doing this training online. It's open source, it's 100% free. Everything is either on GitHub or on social media. I'm streaming on YouTube and LinkedIn. So I was planning to put on some platform, but I didn't want to make things complex and complicated for you to do the registration and things now. It should be easy. You go there, but we have the formatting. So it's like a normal online training. And during those trainings, every week, I send a challenge. The first challenge I'm going to show you here, before we begin, is I have those two tables. You see, they're very simple tables. We have the table method and the table method object. On the table method, we only have the ID, the parent, and the name. So we can think about that when you go to the supermarket. You see the department, the sub-department, and the sub-sub-department, and then you have the products, right? So we have this auto-reference. And then we have the object. And the challenge is to get all this reference here and build a report like this one, where we have the whole hierarchy, the IDs, the names, and the total, the sum of the objects, using one query. The way the application, the developer, they usually do is they select the child. From the child, they do another select to find the parent, and then another one. So if we have, like in this example, that we have 3 levels of hierarchy, the application goes 3 times to the database. I only want one time. That's the first challenge. The second part of the challenge was to make this select work in less than 2 seconds. My original select runs in less than 700 milliseconds. So it's possible to make it to run in less than 2 seconds. The person that won the challenge, his select, runs in 120 milliseconds, 7 times faster than mine. And if you see, we don't have any index. Actually, we do have the primary keys only. And for this challenge, you cannot create any index. You should use as it is. You can only change your select. We are not optimizing the database. We're not changing any parameter. We're not creating any index. We're not changing the model. Nothing. We're just changing the select. and I want it to go down from 2,000 milliseconds to 160 milliseconds, 10 times faster. This is saving money with data model. This is optimization. And you can think about how much money do you need to make your database run 10 times faster? How much memory, how much CPU you need to pay for the cloud computing that you're using? That might be a lot of money, right? So our agenda today, we're going to have an overview. What is this talk about? Probably what is more important is not what it's about, but what it's not about. We're not going to talk here. And we're going to review some old concepts, hard drive, RAM, DRAM, CPU. It's annoying, but we need to understand how they work, to understand some decisions that have been made, not only for Postgres, but some other databases, and for the developers. And some developers, they do use those things, and they have no idea why they're making those decisions. And we're going to try to understand today. We're going to talk about how Postgres organize the data, those heap files. They've been talking here before by OreoloDB. They said they were using it, might be a problem sometimes it's an advantage. We're trying to understand what they are and what they do, and some of problems that we have. For example, how Postgres is able to recover from a crash. Let's say I'm starting a transaction, I'm sorting something, and before I do a commit to rollback, my database crashes. Postgres, when it comes back, we hope it will be able to come back and undo that transaction, roll back that transaction, right? So how is it possible? Postgres doesn't have an undo log, undo files like other databases do. What is the magic here? And if we have time, we're going to talk a little bit about the free space map. It's important to understand how it works, and a summary, and I will come back to that select. And well, we're the last one, right? We should have time. Okay. What this is talk about. As I said, we're not really talking about modeling. I'm not going to talk to you about I forgot the name of when I'm modeling, you have those 3 layers of modeling.
Normalization.
The formal normalizations. We're not going to talk because that's boring. You know, I hate them even though I use every day. I don't like them, that's boring. So we're not talking about this. Here we're more talking about how it stores internally. It's not an internal stuff. We're not talking about code here, how it's done in Postgres, but how it's organized, right? We're going to see how the impact it makes, and we're going to see how that magic happens. Like, remember that in the beginning I said we're going to try to reduce the size of a table from 74, 76 megabytes to 6 something. So how is that possible without changing an end data? And we try to correlate all of the above so we can have some savings, because the main idea of the topic is to save money, right? So this is what we want to do. Okay, let's start with the DRAM, CPU, memory, those things. So this nice picture is how memory is organized. So when we talk about memory for the CPU, everything that is not the CPU is memory. So, but we have different levels of memory, right? We have the very fast register. They're built inside of the CPU. They're really, really fast. They're really, really tiny. So, and then we have the cache memory. The cache memory usually have different levels. So we have the level 1 that is really fast and small. We have the level 2, level 3, so they're getting larger but is lower. We have the main memory, just the RAM, the memory we use. And up to the main memory, CPU is able to access. I mean physically. CPU is able to access all of them physically. Down, when we have here 2 magnetic disks, well, it's an old picture, ignore that, but it still has tapes. So, but the SSDs are down there as well. So there is no physical link from the CPU to the disk. So it means that everything that we need needs to go from the disk to memory. So it can be done by a request from the CPU. CPU can do some work, or it can be done by the disk driver itself. The disk has a device, not only the disk, the main board has a device that controls the disk, the controller. It can pre-fetch data, can preload data. So if the CPU needs that data, it's already memory. So it's free. It's sort of free data that comes from the disk to the memory, because CPU doesn't have to waste time requesting for that data. So, and this is how it's organized. And this is how, when we say that CPU, everything that CPU does should be in memory, is because you have a physical limitation, and it's by design. Literally, CPU cannot work with data on disk, because it cannot access the data there, right? So for the memory architecture here, as we are saying, this is how it's organized, as you see there. So the CPU, it goes to the memory controller, and the memory controller, the memory goes to the disk, to the I/O. From CPU perspective, it can do two things. It can do I/O, and it can do some calculations. It shifts bits from one place to another, or it gets and sends bits. Those are the only two things that CPU is able to do. All the magic that we do here, it does with two types of operations inside of the CPU. Right? Everything that's not calculation, is not math on CPU, is I/O. Sending data through the network is I/O. Saving data to the disk is I/O. Sending data to memory or requesting data to memory is I/O. So we have I/O on different levels here, but everything in the end of the day is I/O. And the I/O, they can be fast, slow, cheap, or expensive, right? So the closer to the CPU, the more we are got, the faster it is, and the more expensive it costs money, but cheaper for the CPU, because the CPU has to work less. CPU does a lot less cycles to do, right? And we basically have two different, when it comes to disk, we have basically two different types of I/O, of access I/O. The data can be accessed randomly. So I think I have something here. Yeah, the data can be accessed randomly, as we see down here. So there's no order, no organization. It's just putting the data in random places. Or the data can be accessed in a sequential way. In memory, the data is mainly random access, because memory is really fast to work with this type of data. In disk, we ideally want to have sequential access, because it's a lot faster to access sequentially the data. And we can do a lot of optimizations, like for example, prefetch. We're going to talk about well, I think I removed. We're going to talk about locality of data. Briefly. So what is locality of data? When we're talking about locality, we have two different types. It's how the data is organized. We have, the data can be on terms of locality. It can be on time, depends on time, or is on space. So the data that I access now has a really high chance that I'm going to access the same data in future. So if I can keep that data close to the CPU in a fast storage, so I can speed up, right? In future, when I need this data. So this is cache. It works with locality, the time locality. The space means if I access the block number 1 or block number 2, the chance that I need to access the blocks 3 and 4 are pretty high, because they're in sequence there, right? So if I can prefetch them and put in memory, I speed up my processing. This is again how it happens for caching, how we do the caching, how we choose which data we're going to put in memory. So we prefetch, because the chance that we have is pretty high. If we can keep the data close to each other, the data that's related to each other close, we can prefetch that information, and we need to read out those blocks that are in memory. So we get them for free, right? And for SSDs and NVMEs, the difference of access, they've been hugely reduced from random to sequential, but we still have some differences. Sequential is still faster. Probably they've been proven, and at some point we have the same, or we split into just like RAM memory, but we still have a few differences. So here are just some charts of difference, how fast and slow was the patterns. So old hard drive spinning drives that I hope nobody here uses anymore. So we see that was so expensive on time to access the data, if it was sequential or if it was random. For example, the same amount of data, it could take 53 milliseconds if that was random access, and 50 milliseconds for a sequential access, and 6 seconds for random access. Those are orders of magnitude. And this is how all the database always try to keep something in memory. Like, that's why we have those buffers, the cache, and some database called buffer pools and things. They try, and even the Linux, we have the page cache. They try to keep the data in memory because, well, 2 problems we solve. If we change the same block multiple times in a short period of time, we don't need to flush the disk that many blocks. We can just flush the block once. So instead of, for example, flush 10 times the same block, if I flush once, I save a lot of I/O. Also, I can reorganize the data if I keep the blocks in memory. So instead of do the random access, I just reorganize in memory, and then I flush those whole blocks close together. So we are working with the locality here. And it can save a lot of time. This is the same chart for difference from the SSDs. So as we see, we don't have that much difference anymore, at least the one that I tested. So those tests was done in a MacBook, so not sure if it's really reliable, but like at least we can see that's why it's not that huge difference. And now that we understand a little bit how the data is organized, how the memory is organized, not the data, how the memory is organized, the I/O, those things, then how Postgres use those things to keep everything organized. How the data is really organized inside of Postgres. When it comes to file organization, we usually have 2 main types of file database uses. So we have the heap files, that was one used by Postgres, and we have the cluster files, usually clustered files, that are one, for example, used by InnoDB on MySQL. So on the heap files, there is no organization on the file. Everything is a block, and you can put everything inside of that file. Like, for example, a table, if you have a table, there is no order for the table. Whatever we set is the order that we insert or update. So we can have no guarantees of the order of the data inside of the table. When we have a cluster index or a cluster file, the file itself will be organized like an index, usually a B3 index. So when we insert the data on a cluster file, we need to traverse the tree and find the proper place to insert that row. So then we can have a few considerations. First, insertion on a heap file is a lot faster than in a cluster file, because as we do not need to keep any order, we just need to find the next free spot and insert the data and save the file. In a clustered file, we need to keep the order of the primary index. So we need to traverse the tree on the file, get the spot. If you don't have a free spot, we need to allocate or order reorganize and find a way to allocate there or create a link. So we need to find a way to do that and then insert the row inside of the cluster file. So insertion is lower on cluster files than the heap files. The problem, like, there's advantages. We may think that search on the cluster file is cheaper than search in a heap file, right? Because the cluster file is organized by the index, right? At least by the primary key. But if we need to do a full table scan, it's a lot cheaper to do a full table scan in a heap file than in a cluster file. Remember that locality thing and the way the sequential and random access. So in a heap file, just because you put one after another, is a lot easier to have a sequential file. You just need to start reading the file from the beginning to the end with nothing specific. If you do a full table scan in a cluster file, it is a tree, right? Usually B3, it's an index. So the file on the disk is like the random one. We need to traverse the tree. So we start from the root node and then we go to the trunks and the trunks until we get to the leaves. So we need to traverse. It's really a lot of random access on the file. That's why a full table scan is so expensive on InnoDB, for example, and not so expensive on Postgres. Because we just do a full read. We don't need to do that many random access. And that's why there are some parameters on Postgres that you tell to the database how expensive a random access is compared to a sequential access. I forgot the parameter, but like it can make your database use more or less your indexes, because when you use an index on Postgres, you're changing the access pattern. Postgres needs to go to the index and traverse a tree. Now it's a random access. And after traverse the tree, it needs to get back to the table and get the data. Go back to the tables, like most of the people believe that go back to the tables and get the data is the expensive operation. Actually, traverse the tree is the expensive operation. Because it's done randomly, not sequentially. And that's why a lot of times the Postgres is going to evict an index. They thought, wow, I created this amazing index here. It serves like I'm using the query on the where calls on the index that I've created here. And sometimes it's a primary index. But like, the databases do a full table scan. Because it's cheaper to just use the equation and get it than traverse the tree. And if you treat the database and tell the database that the sequential and the random access are the same, so then it would be more prone to Postgres to go to your index and get the data from the index. Right? So we have other points here on the way Postgres implements MVCC. This is not related to the heap files only, but also for Postgres implementation of MVCC. We have no deletion on Postgres. I mean, physical deletion. When you delete a data, Postgres goes and mark that data as removed. But the data is still there. It's not removed, it's not wiped out, it's still on the file. That means we can have a lot of garbage inside of the data file. And that's what the people call loads, right? So when you have a lot of deletion, those data that are there will keep the file gigantic. So sometimes, okay, this file, I have 1 terabyte table, I want to do a cleanup. You go there and do a huge deletion on the database, and your file is still 1 terabyte. Well, that math doesn't match, right? It's because Postgres doesn't really do a physical deletion. And it doesn't do a in-place update either. When you do an update of a row, something inside of Postgres, it copies the row, changing memory, and then saves somewhere else inside of the file. When you do an update, you're duplicating the data that you have, and then it marks the old one as removed. So it lies twice. We're not really changing in place, and you're not really removing the old version, right? So, and then when sometimes you have a table that you have like 1,000 rows on that table, and that table has 500 gigabytes, and you have no idea. Because you have so many updates on that table, and it's bolting and bolting and bolting, and you don't have a vacuum process we're going to clean up. And we're going to talk about that. And that table is just gigantic. And you have few thousand rows. And again, the match doesn't match. Right? And those are the regions. Those are the bolted and how we create those huge bolted tables. Okay. Before I go here, one very important thing is CPUs are really interesting and tricky piece of hardware. They have really a strict way to work. They work really well with data that has the same size of the code word. So for example, a CPU of 64 bits has a word of 64 bits. Everything that is divided, sliced is in 64 bits, so that's word size, going to work really well. Because the CPU can do just one cycle, one operation per cycle. Doesn't waste time, because it fits perfectly the space that it has inside of its own registers. If we have, for example, one data that is, on this example, that is 8 bytes, 64 bits, right, 8 bytes. If we have a data that is 9 bytes, it needs to get 2 cycles to process that data. If we have a data that has 15 bytes, we're going to take the very same. So if you can fit your data in multiples of those 8 bytes or 4 bytes, depends on the word size of the CPU, you're going to get the very fast processing of your hardware. So the guys that work with database, guys that develop Postgres, are really smart guys, and they thought, why don't we do those things using everything in the word size, right? And Postgres uses multiples of the word size. And for example, CPU Postgres stores the data on those files using what we call blocks. There are pieces of bytes, and uses 8 kilobytes block. And that has the purpose, because those 8 kilobytes are multiple of those block size, those word size, right? So, and we can organize those things. So, and we're adding them, then we start understanding why some sort of decisions they are made. They're not just random. It's not because I like the number 8. Right? Actually, I do prefer the number 7. But the page size is of 8 bytes. It means that all the data that we have, they are inside of those page size. And Postgres doesn't split the data between 2 pages. If you have something that you want to save, it needs to fit inside of a page. But how about those blob things? Some people, they store huge JSONs that have kilobytes or megabytes of data. How is that possible if it cannot fit? This is when it comes in place what they call toast. Thank you. So they have other files, and they just put a link here, an address for them that goes to all those other files that name it toast. So when you see something related to toast, it's not a snack, right? This is how it goes here. So then everything fits inside of those pages. And those things that cannot fit inside of those pages, they go outside. They go to those files. Right? Yeah.
I actually have a question.
Sure.
I just want to clear my confusion or something like that, but about this heap file. I want to relate that to heap data structure, which is built on priority queues, where you sort a data into the heap, and then of course it gets to the bottom. Then there's a sorting going on where end of the day you have the smallest at the top of the heap. And so now I'm just kind of curious how this compares to heap file. So that when you're putting in tuples into the page or something like that, how does Postgres handle efficiency in retrieving those stuff? Does it relate to this heap file or something else?
No, it's not really related to the heap data structure.
Yeah.
So the naming of it is just this one is just a plain file, sliced in blocks, and you just put the data, and there is no real order like on the heap data structure, right? That's first in, first out, and all this kind of now. Here you have no relation to that. That's zero order is just how it like it's a file, a plain file with no order. We're gonna see later a little bit about this, but has absolutely
No relationship.
no
with
relation.
that.
No.
All right. Cool.
No. And yeah, it's divided in blocks. Another important thing is the max file in Postgres for data file is 1 gigabyte. It doesn't mean that you cannot have a table that is larger than 1 gigabyte. It just means that if your table is larger than 1 gigabyte, we're going to have more data files. Right? So the max one is 1 gigabyte. We're going to sometimes you're going to hear me saying page or block. So their equivalent for what I say is page. So very common to say in the database blocks when you go to IO and subsystem. So, but they gonna mean the same thing here when I say page or blocks. So they have the very same meaning. There is no difference, right? And next one. And those pages, those slices that of data that we have there, they have internally their own organization, right? So they have a header that has some information about the page, and they have the data itself. One thing that we can see from this image here is we have what those items there, those are pointers from the data. The data is not doesn't start in the beginning of the page. The data starts in the end of the page. And in the beginning, we have those pointers. And it looks weird. Like, why should it? Like, I don't just put the data there. Right? Why do I need pointers to the data? Right? And why the data starts from the end and coming to the middle? So it doesn't make much of sense, right? But actually, it's a really interesting organization. Postgres has one thing that they call hot. So sometimes the names that we choose in Postgres are interesting. Like we have post, we have hot. So the hot is the heap only tuple that we change here. What happens is, let's say we have a table and that table has an index. Every time that I do an update on the table, I need to update the index, right? Because it will change the position inside of it. Remember, we don't do an in-place update. We mark the old one as removed and create a new one. So we need to update the index with the new address of that item. But if we do have space inside of this page and the new row fits here inside, you don't need to update the index. You just need to update your pointer because the index has the pointer address. That's a hot only update, the heap only update here. You don't need to change anything on the index. You only need to change on the heap table. So it can make your updates a lot faster. And there are some parameters on Postgres that you can change, that you can tell the Postgres, I don't want to fill my heap tables. I don't want to fully fill. I want you, when it gets to 80%, 75%, you create a new page and start filling that page. So you keep some empty space. Because when you do an update here, you don't need to update your indexes. So you're sacrificing some disk space to improve performance. Right? This is a trick it's quite interesting here. But if the update doesn't have space here and the new row goes to another page, then the index has to be updated. But remember, it keeps the ID, so then it needs to be changed. Okay, now inside of the row. So the row itself, it also has its own organization. It has a header and the data itself. So we have at least 24 bytes inside of the header, because it depends if we have many new columns inside of the table. The Postgres uses a bitmap. You guys know what's a bitmap? Anybody?
0 and 1.
Zeros and one. But like, how does that work? So, as the name says, it's just a map of bits. And we give value for those bits. For example, here I have 1, 2, 3, 4, 5, 6, 7, 8. Okay, let's keep 8. I hope everybody can see. I have 8 bits here, right? So I have 7 zeros and 1 1. So I can give, like, just showing this, it has no meaning. But I can give meaning for those things. I can say that this first bit here means that I have one null value inside of this table. Or means that the first column inside of this table is null or not. So here I can have up to 8 columns on my table, because my map of bit has 8 bits. So with these bitmaps, I can tell you if I have or not null columns, and which columns can accept nulls, or which columns are nullable, has null value inside of the column. So I don't need to keep the column itself. I don't need to keep the space for the column itself, because I can use one bit to do the representation of the null value. And this is how Postgres does. It uses a bitmap, a map of bits, to tell us if here in this row, the column is null or not. Right? So we can save some space. Right? We have 2 columns, and 2 fields actually named T info mask. We're going to take a bit look to see what they mean. They give us some more information of the data. They keep information to say if this data is valid. Like, for example, remember the question about the crash on the database? The thing is, everything that you write to the database goes to the data file. And now we're going to start with our interesting demo. So I have a database here, and I hope it's not running. Oops, I don't want to stop, I want to start. Always keep passwords in your database, even if you only you access inside of your laptop and it's for test for a presentation on Percona Live. Right? So I'm using the database test here. I'm going to create a very simple table. The table is, let me see which tables I have here. I already have Q1, Q2. I don't need to create a table. I can use this one here. So let's check what this table here has. So here we have too many columns. I'm lazy, I don't do that many columns. So create table Q1. I only want to have an ID that is integer and primary key. It doesn't matter because I like to have primary key. It's a good design. Always create tables with primary keys, even if you're not going to use them, like here now. B, just text, and accept. So I created this table here. I'm going to insert into the table T1 a select X MD5. I never remember if it's X text. If it's MD5. And 1,000 rows is enough. Well, that worked. That's amazing. So, one thing that you can do here, T1 limit 5. So, this is what happens when we do a select star, right? We always believe that the database is going to show us all the columns when we do select star. Database, the Postgres is lying to you again. You see, it's lying a lot. It lies a lot. It actually has some hidden columns. For example, oops, there's an extra thing here. We have the CT ID. Where did this come from? Right? Like, we believe that select star is everything. Right? That this is what they tell us when we're doing this SQL. Now we have the CT ID. That's like 0102. What does that mean? Here are the addresses of those data on our file, let's put it this way. The first one is the page. Well, it's not, I think we can get it a bit better. Okay. The first ones here are the page, the zeros. So it's on the first page, page 0. And then the other ones are the indexes, the pointers. Remember the pointers? So those guys are the pointers. Cool. I know the position, but like, what does that mean? What is the point to know the position? Right? And I prepared here a series of really nice selects for our lab. See? You can see that 1 hour probably won't be enough. Well, we won't go through everything. And because, remember, I'm lazy, even to remember things. So we can inspect this table. Remember that it's a very simple table organization. It's not a cluster index. It's just put data one after another in binary format. But we can kind of take a look, take a peek on those things, especially because the table that we have here is very simplistic, right? So let's just get the information that we want here. And I want to check the free space map, not yet. Okay, and okay, this is what I want. So I'm going to use an extension here. That's a very, very interesting one to take a look inside of the table, like to have some information inside of the table. So what I want to see here is the physical position of the data. I see that the line pointer, the index, the first one, because I'm checking the 0 there, is on our first page. The first line pointer, it's pointing to something on the physical address, 8120. This is bytes. The bytes number 8120. And it's telling me the length, the size of that data is 71 bytes. Right? So who cares? Right? We don't need to have that information. The thing is, we can take a look on that thing. But first of all, I need to get my database OID. Well, first I need to know where my data files. Okay, this is my data files. And this is my, oops, actually it's T1. No, this is the database test, and now I want my table name. Actually is, oh, that's unexpected. I just got a card out.
PS equivalent.
Yeah. That was not in the script, right? We're not here to debug core dumps. And my queries are pretty complex, right? It's very complex ones to have a core dump. So that means my PSQL, not the database, but the client, the PSQL crashed. So it generates a core dump. So what I did here is, I want to know my data dir, where the data is being stored. So I can go to my data dir. Inside here, I have a folder base. Inside of this folder base, I have my database. This folder here is my database folder, right? And inside of this my database folder, I have my table. This file here is my table. This is literally my table here. I have a nice tool here, xdump. So I can ask xdump to show me in a nice way using hexadecimal and try to convert to character what it's able to. Some information. I want to start. What was the position here? Let's go back. So this is the position that we want to start, right? And if I'm not mistaken, the position is -s. Yes, that's S. And I want to read 71 bytes, and read is -n. 71 bytes from this file, right? And here's my data. Here's literally my data. You might not believe because that was this. Let's do something better, right? Let's put some meaningful data here. I'm gonna drop table T1. Let me create a table. Oh, I even lost the create table. Create table T1. It's ID integer and B text. And it's a primary key. Not really needed. Insert into T1 values 1. I'm going to insert Charly. 2. I'm going to insert Batista. And 3 is enough. That used to live in China. Right? So I have enough data. Now I need to just get my table name, because we're inside of the here. So this is my table name. And the thing is, I cannot just use this one because, well, the data might have been shipped, right? So like, for example, now we sort of got something in between because, remember, the data has been shipped. We need to know the address of the data. And we can get it because I have this nice select here. Not this one. But you never know what it is. But I eventually, not this one. Eventually get there. Oops, wrong. T1. Okay, it's a start here. Now we go. Oops. Start at this position. And this data, we want 35 bytes. So this is what we have. See, now we have Charly there. Now it's easier to see. And funny thing is, remember we have 24, that is the header. So this is the header. The next one was the ID. It's an integer, it's a 4 bytes. Right? And then I have the other bytes here. Right? See this information here, that they have 1, 2, 3, 4, 5 bytes. This is waste. It's not being used because if we check here, the next position doesn't match if we add or subtract 8152 minus 35 is not 8112. This is because of alignment, or as we call padding. So the database will fill with zeros. This is 35 plus 5 here, right? So 1, 2, 3, 4, 5. 42, the next one. Yeah, see, it's filled with zeros. Everything filled with zeros. So all those paddings, they can hurt back. Right? Well, we're running out of time.
How much time do you have left in the presentation?
Well, I can hurry up here. So what I want to show here is how this can hurt us, how this padding thing can hurt us. I'm going to create this table here. It's a very simple table. So I drop if exist. I create that table. I'm going to insert 1 million rows. And I'm going to create another table, exactly this very same table here. So I'm going to do a checkpoint just to make sure it's on disk. So the first table create TQ. So it's like a queue table where we have type ID, we have another ID, we have a boolean. So it's a very common table, right? So, and the only thing that I did is to reorganize the tables here to put the integers that has 8 bytes together or integers that has 4 bytes together. So the types that has multiple 4 bytes together to fill those 8 bytes. So we don't waste space. We don't have that padding. And if we check here, if we do the select, the first table has 73 megabytes. The second table with the same data, because we created using a select for the first table, has 53 megabytes. The only thing I did here was organize the columns to remove the padding. Those zeros that was waste of space. Here we are saving data, we're saving space, we're saving memory. Remember, when you go to application, this data needs to replicate. We're saving, making your application faster. We're saving bandwidth, we're doing everything. We're saving a lot of money. And this is how we can save that money, a lot of money, just changing the model, the way that we organize our model. For the application, it doesn't matter where the column is on that table. But now for us, for the database, we can save a lot of space. We can save a lot of money. And this is how we can use our data modeling to save money on Postgres. As we're running out of time, thanks for your attendance. If you have questions, we can talk later. And thanks again.
Yeah.